Okay, then, thanks very much for coming to my session about the Intel developer tools. Before I start, we have T-shirts in the back, so when you are leaving, please take one. There are 3 different sizes. They are enough for everybody, so you don't need to hurry. So my name, Heinz Bast. I'm working with the Intel Software and Solutions Group in Munich. And we typically support developers like you, ISVs as we call them, and I did even support game developers a couple of years ago. But just now I'm working more for enterprise-like applications and high-performance computing. Today I would like to introduce some of our developer tools, but I will restrict myself to one of our libraries, IPP, and the VTune Performance Analyzer, which for sure is the focus of this talk. So about 2/3 of the presentation will be about VTune. And if you have time at the end, I would like to show you a few slides about our threading tools. For the introduction, so Intel has a couple of tools. You see them here on one slide. Some very specific tools for the... Okay. Some very specific tools like the... denn der sehen die mich nicht mehr. Das ist blöd. Da gehe ich da hin, warte. Probably better. It's okay. So some of our tools are very specific, and you probably will not touch them in the context, like for example demo tuning. But in case you are working on this HPC cluster tools, we got them by acquiring a German company near Cologne, Pallas GmbH, last year. Here, the availability of all the tools. You see, we are not providing these tools only for the classical architecture. You typically are working on the legacy architecture, IA32, Pentium 4, Xeon, but we have them too for our Itanium architecture, and we have them even for the X-Scale and smartphone PDA. And there are a few gaps, like for example, our threading tools are currently not available for the Itanium architecture completely, but we are closing them in the next couple of months, and the beginning of next year they should be complete. 1 or 2 slides about a transition just now happening at Intel, and not only at Intel. So we are moving to dual core in this year, which means whenever you buy a processor from Intel, you will get 2 of them. So we are talking about sockets now, and each socket contains at least 2 cores at the end of the year. In the future, this might be extended to 4 or even more. And this will even happen for our laptop in the next, let's say, 24 months. And all our tools will help you to move your application to this new environment. For you, it's nothing else than programming for SMP system, shared memory processing systems. So like having a dual Xeon system today, you will program for the Pentium 4 or whatever it's called in the future. You see here, for example, these thread checking tools or thread profiling tools, they are specifically designed to help you to parallelize your program, to multi-thread your program, to debug it, and to tune performance for it. But also all the other tools have a component specifically for this multi-threaded environment. So for example, all our libraries are multi-threaded internally. So you get very easy this SMP parallelism by simply using our libraries. Don't need to invest much. So the first part of the talk is about one specific library. So in total, we have a couple of these libraries, like for example, MKL for HPC computation, number crunching. More interesting for your environment, demo tuning is our multimedia library, as Intel, as it's called now, Intel Integrated Performance Primitives. And I would like to spend 2 or 3 slides on this library. So this library has a couple of domains which are supported, like for example, image processing, JPEG, security, cryptography, JPEG, video, audio. So whatever you're doing in this area, we have these routines in this library. There are about 11,000 routines today, and this library comes with sample codes. You see this on this second layer here. So for example, you have almost a complete MP3 player, or a JPEG encoder, or a video MPEG-4 decoder, and so on. It comes with the library, and it makes it very easy for you to port your application to the specific architectures of Intel. So for example, here you see the classical architecture indicated by 4 blocks, which means that this library is not only tuned for this IA32 architecture, but we even have a special version for Pentium 4, Pentium 3, the old Pentium 2 and so on. So you can really get manually optimized code for each of these architectures. Very easy way to get optimal performance. And here one example, an MP3 decoder. So if you would like to implement this, you simply check your pipeline, the pipeline you want to implement in your application, and then you identify the hotspots, those parts of your application where most of the computation time is spent, and then you simply can select the corresponding routines from this library. And in total, I think it's here, you get over 90% of this computation realized by this IPP library. So you don't need to care about optimizing, for example, a digital cosine transform, whatever. You get these routines in our library, and then it would be very difficult for you to write faster code. So we have hand-coded assembly instructions in this library and optimal tuned by people who know our architecture in very detail. So I would like to close this library now after I show you this benchmark slide or performance slide. You see here in this block diagram the performance gain compared to optimal handwritten C code. This is the factor 1 here. So if you would write your, for example, a JPEG encoding routine in very good C code, you would get this 100% or factor 1. And then here the bars are showing you the performance gain you get if you use a Pentium 3 optimized version of this IPP routines or a Pentium 4 optimized version. So this can go up to a factor of 8 to 9 here in the audio area, which means that even if you write good C code for, let's say, some audio transformation code, linking IPP instead of your C code, you might get a factor of 8. So this is done by really hand-coded assembly and really using every feature we offer in our architecture. For all the other domains, it's not this much, but you still see typically 200 to 300% as normal gain. Additionally, the slide shows how much we really optimized for the specific architecture. Here, for example, it's a very extreme case, speech recognition. Choosing the wrong library or library version, let's say you take the Pentium 3 library and you run this here on a Pentium 4, you don't get the benefit you would get in really using the right library, specifically optimized for the Pentium 4. Okay, now, any questions to the part up to now? Otherwise, I would move to the feature.
What was the original code made from? What kind of C compiler was used?
The Intel compiler. So our compiler. By the way, I don't talk at all about the Intel compiler, but due to lack of time. But we have the CDs downstairs at the reception, at the registration. And if you would like to test our C compiler, for example, you simply can link them into the Visual Studio environment. It's 99.9% compatible to Microsoft's compiler. So you might get an additional performance win. And we have a couple of features not available on Microsoft compiler, like, for example, OpenMP support. And we support a couple of intrinsics which are not supported by Microsoft. So try it. Okay, now going to VTune. So whenever you do in your professional life or now here at the demo scene, you're trying to optimize your application. You are typically moving in the circle. So you start selecting some typical benchmark, some application, some test, which is realistic for the final outcome of your application. You identify some hotspots where a lot of time is spent. You try to investigate why does my application spend this much time here. You try to improve your code. You test it again with a benchmark, and then you might not be satisfied with the results, so you go on and again. And finally, you have reached the final result you're looking for, and then you can get a beer, or ask for a salary increase. So, but the question is here: how do you identify your hotspots, and how do you understand why you have this hotspot in this specific part of your application? And here is where VTune comes in. The VTune tool helps you first to identify really those places in your application, those source code lines or even assembly lines where you have a hotspot where a lot of computation time is spent. And then, very important, it too helps you to fix this problem in case it can be fixed. So now a rather complex slide. The VTune tool supports not only IS32 but also the new 64-bit Xeon architecture or the Pentium 6 XXX. It's our latest release of the Pentium 4 architecture supporting 64-bit too. Of course, our Itanium architecture, even the PDA smartphone, PDA X-Scale processor. We support Windows, but we also support Linux. We support explicitly .NET and .Java. So for almost every popular environment, vTune is usable. Additionally, there are two modes of how to use vTune. First, in general, you are using it natively, which means you are using vTune on the same system you run your application on, for example, on a Windows system. But we also support environments where it is not this easy to run vTune natively. For example, old Linux releases or your PDA, your smartphone. And we do this by what we call remote data collection. So you run a collector on this target architecture, but you analyze the application on your Windows laptop or whatever. So you install Windows, or you install vTune on your host system, and then by a simple USB or LAN connection, you can monitor, you can analyze your application running on a remote system. Here, all the four features. I come to the most important one in later slides, so I simply want to give you here an overview, and don't try to read the small stuff. It's not relevant here. The most important feature of vTune is what we call time or event-based sampling. Here, vTune samples events happening while your application is running. This is probably the most important feature, and we will come to this in detail in a few slides. The second one is what we call call graph feature. Here, you can very easily check where most of your time is spent regarding the modules of your application. You get a nice tree of the call relationships, we will see in a second. Then, only available on Windows, you can monitor, for example, events like the number of page faults your application is causing, or the number of packets sent on the network, I/O requests, whatever. This is similar to what Perfmon on Windows offers you too, but you get it here displayed in real time in a nice graphical way. And then last but not least, there is an expert system like tuning assistance, which looks at the data you have collected, it looks at your source code, it gives you very specific instructions on how to fix the problem. And we have here the explicit support for C++, Java, and of course for assembly instructions. Here, a few views on the different features. This is the sampling view. You see, for example, here in the hotspot view, you see events displayed against the modules of your application. You will see this in a full screen slide in a second again. Call graph here, you get a tree representation of your program flow. Each of these nodes represents one of your program modules of your units, like a C function. Here the counter monitor, you get the events like page faults displayed against the time on a horizontal axis here. And so, for example, you can monitor on what's happening in your application while it is running regarding page faults and so on. And last but not least, the tuning assistant, which gives you very detailed instructions based on the events you just collected. So I come to this again. So again, as I mentioned already, most important in vTune is sampling. So what does sampling mean? You try to identify typical performance bottlenecks in your application while it is running. And we make a difference between two kinds of the sampling. The first one, the times sampling. This is the most trivial way to use vTune. You simply look where is the time spent while my application is running. So for example, you want to see in which source lines or in which loop is most of my time spent. This is probably 95% of the way vTune is used, and I think this is a pity. vTune offers much, much more. So this is the most trivial way, but on the other hand, it's the typical way users use vTune, but because they don't want to invest more to look at the details, and they are hidden here in this processor event sampling, which, for example, allows you to look for branch problems in your application, cache hierarchy problems, and so on. Somehow, time-based sampling is a specific case of this event-based sampling, because if you take this event processor cycle spent as the event to monitor, then you have time-based sampling. But in some cases, you can't do this, for example, or you get problems. For example, if you have a system with hyper-threading, then this time-based sampling can give you very confusing results, because you have two threads running in hardware, and both add to the number of cycles. So sometimes a pure time-based sampling where you use an operating system timer is much better than using this event. So we have this documented in all detail in our manuals. Okay, now what sampling, what does it mean now? It is some kind of a statistical process. You interrupt your application in very small time intervals, and then you collect the data. First, you collect the time when this sampling occurred. This is important to really map this data later to your execution time frame. More important is the spatial information, the information about where the event has happened. So for example, you want to know on a multiprocessor system which processor. You want to know which process, in which module. Is it a DLL of your application? Is it your application itself? You want to know which module, which thread, and last not least, most important probably the IP address. So you want to know exactly where in your program it happened, which simply means the content of the instruction pointer, so that you later can really map this event against the source line or even the assembly line. And here, how it happens. So if your program is being executed, then every small time interval, let's say 1 millisecond, your application is interrupted, and then it is checked against the events which have occurred in this interval, and then simply by statistical mapping, VTune somehow does some kind of it extrapolates this data against the overall runtime of the application, which means, for example, you set one of these counters to give an interrupt after 100 events occurring, like for example 100 level 2 cache misses. Then the statistical measuring of these events gives you later a very good indication on where, for example, regarding your source code, this event has happened. You might argue, okay, this can't be very precise, but in the practice it has proven that it's to 99.5% really accurate, so you get really very precise data regarding this event. Also, it is a statistical process, so it's not 100% correct, but for pragmatic reasons, for your tuning efforts, it's 100% okay, and you don't have a problem. Again, here, you can influence all these details, like for example the interval in which you do the sampling. You can increase the buffer size you want to use for this data you collect, and so on. We don't have the time to go into all the details, but all this data can be used either as a default. VTune uses very intelligent default values, but you can change them and adapt them to your needs. So here in the big screen one, look at this sample data. So after you have done your sample sessions, you get typically the events which are listed here displayed in a way we call hotspot view. You see these graphical bars again, here in this case displayed against modules of your program, for example DLLs in this case. And here, for example, you would see there is a hotspot regarding the event level 2 cache misses or cache reads. And a very easy way to find these hotspots on a high-level view. But there are hundreds of views available in VTune to go into more detail and to structure the data. So here probably a very popular view, you can map this data against the source line of your application. So here probably difficult to see from the back, but here you have the level 2 cache references, level 2 cache misses, instructions retired, and clock ticks, so the time spent. And you see the number of events displayed against your source line. So you very easily can check, okay, here in this loop, here in this statement, I have this many events. Typically, the absolute numbers, like it is printed here, doesn't help you much. So it's very difficult to get an immediate understanding from such a huge number, billions of events. But you can display these events too, let's say, for example, in the percentage of the overall occurrence number, or whatever you like. So there are different ways to look at the data, and the percentage view is probably the most intuitive one. One of these features, I mentioned this before, that we are collecting the timestamp of these events too, is useful when you want to look at your data regarding the time. So not against the location regarding your program, but against the execution time. And this is relevant if you look at the first slide here in the upper left corner. Here it's trivial. You have an application running on 4 processes, almost identical distribution of the instructions being executed. Nothing really interesting there. Everything is fine. But if you look at the this slide here, you see that while your program is running, you have a phase here where suddenly the number of instructions being executed in a given interval is going down a lot, and this might be a reason for you to look into your application to check what is going on here. Typically, for example, and I think this is from a Java application where suddenly the garbage collection is started, and this might affect your performance really negatively, and you might want to get this out of your execution time, so increase some buffer or use some different option. In a typical transaction processing system in the enterprise world, this might be real critical, because here in this phase, users connecting to your, let's say, online shopping system might experience a very long delay, and this might affect your business. So it's very critical for you to find this part mapped against the execution time. So this is a completely different view, and it can be easily as confusing as here on the right side, where you have a non-stable behavior at all. So it's very undeterministic, and there you have at least looked for more reasons to find additional causes for this unstable behavior. I don't want to get the Linux people, so we have this sampling GUI, graphical user interface 2, on Linux today, being integrated into the Eclipse environment. Eclipse is a very popular IDE now for Linux. Most companies are supporting this, and this is more or less identical on what I presented before from the Windows view. So you get your events mapped against the source line, so you don't need to have Windows. You can run natively on Linux. Visual 2. Last slide here about the advantages of sampling. So first, there's no need for you to modify your code. You can do it immediately, and you should never lower your optimization level, because you want to check the release version of your application. The only option you might want to add is the option to generate debug information, because if you want to get the source view, we need to have the line number information to create the mapping. Another advantage is you are not restricted to your application. You get also, for example, the events happening in the kernel or in the DLLs you are using, which means you get a real overall view. Of course, later you map these results to your specific application, so that you only get the results which you are interested in, but the data collection is always system-wide. Disadvantage is you can't use vTune more than once on a system. This is an issue on a big Linux system where you have 20 users logged in, so always only one person is able to use it. And then of course here, very important, extremely low overhead. It's less than 1.5 to 1.8%, so that's almost not measurable. The second feature of vTune is the call graph. This is a completely different technology. Here, your application is instrumented before it's being launched, before it started. And so we copy the binary to some hidden place. We modify your original binary by adding instructions to your code for each procedure call being found in your binary. And then the application is executed, the instrumented binary is executed, and you get a very detailed statistics about all the information related to the modules of your program, like the time spent in it, the time the function spent waiting, for example, on a semaphore, on a lock, or whatever. And this even includes the DLLs, but of course not the kernel or the Windows operating system. Here the only option needed to do this, to use this, is you have to make sure you have well location independent code, because we, as I mentioned, we changed your binary, and so the code you generate has to be position independent. And since we are moving this, we are adding something. And here, how it looks, so the Windows view is similar. You get a tree starting on the left here by your main program, and then each of this module represents one of your functions in procedures. Whatever language you are using, can be Fortran, can be C, can be Java, whatever you have. And then this block here, if you go with your cursor on one of these blocks, you get a detailed information which is presented in the table you see here on the top. So for example, you get the number of calls this function has been executed. You get the number of seconds which have been spent in this module. you get the number of seconds spent in this module and all modules being called from this module. So very detailed information. And then additionally, you get this, as what we call critical path displayed by this blue dark path here, which means this is the most critical path in your call graph regarding execution time. So you should start your optimization selecting one of the modules on this path. This brings you the most benefit. The disadvantage of this call graph, I don't know if I have this on the next slide. No, the disadvantage of this call graph is that it's intrusive somehow. In the worst case, it might be a factor of 4 to 5. So different from sampling here, you see an impact on the execution time. So you shouldn't take a run which takes normally already half an hour. So try to find a sample run which takes, let's say, 1 minute, and then call graph might be done in 2 to 3 minutes. One slide about this tuning assistant. Again, you measure this data first, and then vTune helps you with the knowledge about the processor, about your application, and about the data being sampled or collected before. And it gives you very detailed information. So even if you are unexperienced regarding our architecture, regarding vTune, you get a lot of information. Typical example is you have an if then else block in your program, but you have put the most frequently executed part into the else part. Then this is a disadvantage, because every compiler assumes that the most frequently part is the then part. And so the branches are set up in a way that this is the block which is most executed, which means branch mispredicts are less likely. But if you, in your program, are doing it the other way around, so you have your most frequently part in the else part, then you get more branch mispredicts, and vTune not only detects this, it will tell you explicitly, change the order of the then and else block and negate the condition in your if expression. So it's very easy, very trivial suggestion to get rid of this performance problem. For others, it's much more complicated, but anyway, it gives you this information whenever possible. So now, how can we use vTune really to help you to tune your application? The first way is, I mentioned this already, and this probably is what people most of the time use. You simply look, where is the execution time spent? This is easy. You don't need to know anything about the processor. You not even care about which processor you are running on. The disadvantage is it doesn't give you any information on why your application is taking this much time on this specific source line. So it gives you all the information, but it doesn't help you for the next step. The second way to look at your optimization or to help to use vTune is that you look for certain fractions or ratios of performance events. And the most popular one is CPI, clocks per instruction. So you want to know, in average, how many clock cycles are you using for executing an average one instruction. And you can base your whole performance tuning project on getting this value reduced. So you start, for example, on our Pentium 4 architecture by a value of 2, and you would like to get it to a factor of 0.8, for example. Now we have a superscalar architecture, so you can even go down to 0.5 or whatever. So this is an approach. For a numerical application, very popular is this ratio floating point operations per memory access. Others are, for example, the ratio of your level 2 cache misses regarding all the level 2 cache accesses, a very important number. So you can base your whole optimization project on getting one of these numbers optimized, reduced. The third way, you really look for this architectural events, as we call it. So you spend a little bit more, you investigate a little bit more by, for example, checking your branch mispredictions. You want to understand, why do you have this many level 2 cache misses? Why is your pipeline flushed this many times? And many other events. I'll show in the next few slides in a little bit more detail. This requires some understanding of our architecture, so you don't get this for free. But on the other hand, this is the most detailed way, and the way you really find all the performance problems you might have in your applications. Before I go into this, this is one slide about the hardware really being used by vTune and some other tools to make this performance analysis possible. We call it PMU, Performance Monitoring Unit. All modern processors have some kind of this performance monitoring unit. This is the structure of the hardware we have on the Pentium 4. So you have a lot of this registers here on the left side called ESCRs, Event Control Register, Event Selection Control Registers. These events can be defined before you run your monitoring session with a lot of bits, and I don't want to go into all the details, of course, but you can filter them, you can set masks. You can, for example, select that you only want to collect the events from one thread of your hyper-threaded application, and so on. And then on the right side here, you have these events really counting your event numbers, and they are called your CCCRs, counter control registers. I don't know what the third C stands for. You see here that they are always grouped in pairs. This is because we explicitly support that you collect this data independently of your two threads running on a hyper-threaded system. So that's why you always have them doubled here somehow. And this registers, this hardware now can be used to monitor the pipeline of our Pentium 4, the inner workings of the current architecture, in all these different stages here, starting on the left, where you have the trace cache of the Pentium 4, then renaming the registers. Now we have an out-of-order execution engine, the scheduling part, then where you do the operations really, where you execute your integer operations, where you execute your floating point operations, and then very important, where you write your data back to the caches. All these parts of the processor can cause problems when you run your application on it, and this monitoring hardware I presented before helps you to detect this. So they are somehow attached to these components, and there are many, many events. I only have listed here a subset. These are about 60. In total, we have about 140 of these events on the architecture. On the Itanium architecture, 64-bit, we even have 680. So there are an enormous number of events, which gives you really every detail on what your application is doing while it's running. And I have selected here 4 events, which is the second level cache load misses, the write combine buffer stalls, and then bus data ready, and a fourth one, memory order buffer load replay retire, to give you only a high-level introduction on how these 4 events can be used to check for performance issues in your application. Let's start with this write combine buffer. So many people don't know that on the architecture we have additional buffers between the level 1 cache and the level 2 cache, which are used to buffer the data. The level 1 cache is extremely fast. We can access data in one cycle. The level 2 cache is much, much slower. And to be able to, for example, implement stores of your data back to memory in a very fast way, there has to be some buffering between the level 1 cache and the other hierarchies in the memory hierarchy. Here, especially important for you if you are doing graphics development, graphic frame buffer memory is different kind of memory because, for example, you can't cache it. It would be impossible to use frame buffer memory by caches, because you would always have these holes in your graphical application because some of the data would still be in the cache. We call this kind of memory write combine memory. So this data is always written immediately from the level 1 cache to the memory. On the other hand, the typical memory where your application data is located in is called write back memory, and this of course can be buffered in the level 2 cache or even the level 3 cache if you have one. And to enable this faster, we have these buffers in between called write combine buffer. As the name says, we want to combine writes to your memory so that we have in total 64 bytes here in each of these buffers. And if you write only, let's say, 1 byte or 6 bytes, then these buffers wait until you fill them. And then typically in your application, you're not writing only a single byte, you're writing in a loop, for example, a piece of your frame buffer, and so you're adding 1 byte after the other, and then only when this buffer is filled, it'll get written out to the cache or to the main memory. However, if your application is not behaving well, it can be that you have to flash these buffers before they have been filled completely. So for example, assume you are writing only 1 byte in a certain area of the memory, then you are moving to the next and so on. You don't get these buffers filled. And since we only have 8 of these buffers in the latest architecture, then if you do this 10 times, then you have missed at least twice the buffer, or in other words, you have to do a partial write. You have to flash buffers which have not completely been rewritten. And this can be a major performance impact. And there is an event specifically for this kind of penalties or issues you might run into. So for example, if you are looking for issues regarding this write combine buffers and your graphic memory, the frame buffer memory, then you simply look at this event. So you select this event in vTune, you run your application, and if this number is not extremely small, then you have an issue. Typically this issue is if you have a big loop in your application and writing to more than 6 times to different areas in your frame buffer. So you have 8 frame buffers, 8 write combine buffers, but 2 of them are typically always updated, so they are written out and the data is updated to the next level of your memory hierarchy. So a good heuristic is to reduce this to a number 6, and many people don't know this, so they have about 10 or 12 pointers writing to the frame buffer, for example, at the same time, and then you're running in this issue which really can kill your performance. And without a tool like vTune, you would have a real hard time to detect this. The second example I would like to show you on how to use vTune is the what we call store forward violations. When I showed you this picture of the Pentium architecture, it's really simplified here. The store units and here for the floating point data, they are not writing directly to the level 1 cache. There is an additional buffer called memory reorder buffer or a memory order buffer. The reason for this is if you are doing a store to some memory location and you want to read and use this data the next instruction or a very short time later, you don't want to wait until this store has retired. You don't want to wait until this data has been moved to the main memory, which is 200 cycles. You want to get this data before it's really written out. So you want to recycle the data. And this is what we call forwarding. However, there are certain regions, conditions which have to be fulfilled to make sure that you can forward this data to the next read you are doing. And look at your application, the application you have written. This is not an exotic situation. This is a normal situation. So you are updating some data, and a very short time later you are reading this again. And if you can't reuse this data from an internal buffer before it is really written out of memory, then you are lost. The performance is awful. Today, luckily, all the modern compilers like the Microsoft compiler or the Intel compiler, even GCC on Linux, they are doing a very good job to avoid this completely. But in an environment like you are working in here at this event, you're trying to pack all the data, and then you might violate these conditions without knowing it. And so you might have a real bad performance impact. And typically, one of these excess is like having a time delay of 50 cycles. A pipeline has to be flushed and so on. And this is a lot. You can execute at least 50 useful instructions if you wouldn't have this problem. And to detect this, we have an event called memory order buffer load replay. Simply load replay because you have to redo this load because you had an issue in the first time. And here are the conditions in detail on when this happens. So, for example, you are writing here some data, an 8-byte data, and then very short time later you are reading the first 4 bytes of it. That's fine. Works. The same, of course, if you have something like here, works too, no problem. Here similar. So if you have your load data being larger than what you have stored before, but again it has to start on the same address, again fine. However, there are a few cases where it doesn't work. So for example, you are storing 8 bytes back to memory, and then you are reading the upper 4 bytes, so not starting the read and the same address as you did the store. Then you get a so-called store forwarding violation, and this adds one of these events, increases this event counter. similar to here. This doesn't work, so you're storing some data and you're reading a bigger part than you have written before, and so on. So yeah, there are a couple of reasons where it still can happen today, but it's not very likely, but it's worth to check it, and without a tool like VTune, it's get difficult to find these problems. Before I go on to the next two samples, the last two samples, most important on all modern architectures is to optimize the memory access, because the processors are this fast today that typically the memory access is the bottleneck. So your application performance in general is limited by accessing your caches, level 1, level 2, level 3 cache, by exceeding the bandwidth of your frontside bus, and then probably running even into a problem with the latency of your memory, of your DRAM, and so on. And to optimize for this requires some understanding on how all these components work together, but it's worth investing this and trying to understand it. Before I go to one of the events related to this, a few words about prefetching on our current Pentium 4 architecture. So prefetching is extremely important. You want to somehow close the gap in accessing data to memory, which is 200 to 400 cycles, depending on your architecture. And one way to do this is to use data prefetching. So data is moved into your caches before you really use it. We have three types. The first one, and this most people don't know, but it's very important to understand it. The level 2 cache, the cache lines on our architecture is split really into 64 byte halves. So we have a 120 byte cache line, but they are split into 64 byte lines. And if you access one of these 64 byte halves, the other half is prefetched in automatically. So this is what we call adjacent sector prefetch. We call these two halves in the cache line sectors. The second one, this is probably what most people know. This is the normal hardware prefetching. If the architecture realizes that you are accessing some memory area in a regular pattern, then the third time it already starts this prefetching and it gets you in the rest of your 4 kilobyte page. So this is the most efficient way, the most used way, and this increases the performance of your application, even if you don't know about it at all. So it's running transparently in the background. On our architecture, we can have up to 4 of this prefetching streams running in parallel. And then, last not least, there is the software prefetches. The Intel compiler doesn't use it today anymore because the other tools are this efficient that there are only very rare cases where it really would make sense to add explicit prefetch. You can do this. We have the intrinsics, which makes it very comfortable to use them, but by default, the compiler doesn't generate them anymore. In this context, prefetching is important because you shouldn't forget prefetching if you analyze the application of the performance of your application. Because, for example, a prefetch generates 2 cache misses in the background. So you see cache misses caused by prefetching, and you have to make sure that you don't confuse them with cache misses really caused by your application. So there are ways to differentiate them, but you should know at least that they are there. So here, one example of this events related to the memory hierarchy is the level 2 cache load message. Here's some empiric value on what you should consider an issue. So if you have more than 5% cache misses, then you have a problem. So this is some kind of heuristic. Other people say for a very good tuned application, 2% is already the threshold. So if you have more than 2%, you should look into it. Again here, having this cache miss is very expensive. It can cost you up to 500 cycles, but it depends a little bit because on the Pentium 4, up to 126 instructions can be executed in parallel in the processor pipeline. And so in most of the times, there is some other useful work to do, so you don't see really this full penalty, but it might be an issue. And this is very important to reduce them. So some kind of cache blocking in your code. So you should be aware of the level 2 cache sizes, for example. There are ways to ask for them by checking the bits in the processor. So you can really dynamically adapt your application to the different level 2 cache sizes being implemented in modern architectures. So, but cache blocking is the best way that you avoid this level 2 cache misses. But again here, if you try to interpret the data, make sure you understand that prefetching influences this measurement too. And here, very important, the mistake many people make, a write is first a read, because if you do a write to some data element, the corresponding cache line has to be loaded into your cache first, because you can't simply update something because the neighboring element might have been updated a short time before, and so you have to load the cache line first, and then you write, and then you have to write this line back. So this takes twice the bandwidth of your frontside bus. Yeah, and the last event I would like to show you is the frontside bus utilization. So this is one of the most critical bottlenecks in modern architectures. So we have about 6.4 gigabytes per second on the Pentium 4 architecture if you have an 800 megahertz bus. And this can be the bottleneck. And in general, it's very difficult to check on whether you have a problem here. So again, there's a very easy way. If you use vTune, there is an event called bus data ready. And if you simply take this value, you use the simple formula here. By the way, all the stuff is documented in vTune online help. And then do the simply multiplication. Of course, you have to know which frontside bus your system is running and so on. But then you get the frontside bus utilization in percent in a fraction. So for example, if you get a value like 70%, then you have the problem, because even for optimal tuned application, you won't get more than 80%, 75 to 80%. So this gives you a very quick indication on you don't need to tune your application anymore regarding processor speed. You have your issue in accessing the memory data. And so without vTune, how do you find this out? Okay, so that's all what I wanted to present about vTune. I have 2 slides about the threading tools, or 3 slides. Is there any question for vTune? Okay, can do it in the end. Threading tools. This, as I mentioned already, are specific tools from Intel used for optimizing multi-threaded application. We got these tools from acquiring a company called Cook and Associate somewhere in Chicago area. And today they are available as a plugins for our vTune tool. So you install vTune and then you install these plugins. The first tool, Thread Checker, is used to check your multi-threaded program for correctness. The second tool, Thread Profiler, to tune this application for performance. Of course, these tools are very much dependent on the API you are using, and we are supporting today the Win32 threads and OpenMP on Windows, and correspondingly the IF32P threads and OpenMP on Linux. However, on Linux today only in this remote data collection mode, so you can't run these tools natively on Linux, but we are working on this. So this is a huge effort, a huge project at Intel. It's a more or less a complete redesign of the tools to make them working natively on Linux, and we will be there beginning of next year. So one picture about each of these tools. So this thread checker, so you have your application multi-threaded by, for example, using Win32 threads, and then you have the feeling that your application is not working correctly from time to time. And if you have ever done this, you know how difficult it is, especially if these are not deterministic problems. They are very difficult to nail down, and this thread checker tool, by some kind of instrumentation similar to Purify, if you know Purify or Valgrind on Linux, it's checking your application, it instruments your application, and it checks, for example, memory accesses. And then you get a list after running this application with all the potential problems. So for example, here it tells you that a read to a memory location might happen by thread 2 without thread 1 being able to define this variable, this element. And so these are very difficult to find errors. And not all what here is listed is really a bug, but this tool is very, very easy to use, and you get a very good experience, a feeling for what really is an issue. Typical situation 2 is a deadlock. You have a classical deadlock in your application, so threads are waiting on each other, releasing a lock, a semaphore. This tool discovers this really very, very fast and reliable. So this tool helps you to find bugs in your program. The second is this thread profiler. So this is our VTune for multi-threaded application. And there are many, many different views on looking at the multi-threaded performance of your code. One example here is called critical path utilization. So here, an application is running on a two-processor system. It starts by the initial thread creating two threads, and then this two thread is running into a lock here, and this thread is waiting on something until it's released here, and then so on. It goes on. Here you see the time displayed, and then you get this path displayed in different colors. So here you see this on the right. So for example, the yellow serial, you see here a segment of your timeline where only one thread is running on a two-processor system, so this is not nice. So it's marked here by a special color, yellow. Then you have an area like, for example, green, which is very good. You have two threads running on a two-processor system. It's an optimal situation. That's what you would like to have all the time. Then you might have situations where you have undersubscribed. So for example, this is when you have on a system, let's say with 4 processors, you have only 3 threads running. To make this different from serial, which on a 2-processor system, serial and undersubscribed is the same, of course. Then additionally, you see all the locks, releases, and so on, of course. And here again, this tool, of course, requires an exact understanding of the API you are using to understand where you are doing a release of a semaphore, where you are doing a lock, and so on. So that's why it's really important that you either have to use the OpenMP MPI or the Win32 MPI, Win32 API. Additionally, this view here gives you the immediately the information on where you should optimize your code. You see here this so-called critical path displayed as this path without interrupts. If you would try to reduce the execution time here, it doesn't help you at all. It's useless because the overall execution time is not influenced by how long this takes unless this would extend to here. So this special view on the performance of your application gives you an immediate indication where it is worth to invest something improving performance. And so there's a lot of information in this slide already in this view, but there are many, many others. So you get all the details about time spent in logs, times threads are blocked because other threads are not releasing their log, and so on. So this is the second tool we have in this context. Yeah, and then my last slide, summary. So we have the Intel Developer Tools, the latest version on a CD down at the registration desk. So take a copy. And then very important from my point of view, I really would like you to use VTune not only for this time-based sampling, but spend a little bit time and really look for the architectural events. It is worth doing it because you will understand not only the processor, but also your application and how it is being mapped to this processor. And without VTune, it's really difficult. So that's how I want to close my session. Any question? Oh yeah, do we have a microphone? Oh, but he took it. Yeah.
What is the penalty if you're using VTune? You want the events to be identified in the code. You have to get the bug information to code. Is there any penalty?
You mean the penalty on using VTune to find an event?
No. The penalty of getting the bug information with the code.
I still don't know. You mean by sampling?
Yeah.
It's 1 to 2%. This is more or less nothing. It's really non-intrusive. It's in the tolerance of measuring the performance of your data. So sampling is almost non-intrusive. It's optimal. Was this your question or?
Not quite, but I asked you.
Okay, sorry.
Does the thread profiler require the application to be OpenMP, or does it work with Windows API?
the Windows 32 threads and or OpenMP, and partially even combined both. But then it gets dangerous then. But it's possible. Yeah. So and we have no plans at the moment to extend this to some other API. I think there is nothing really being popular on Windows except Win32 threads and OpenMP. Intel itself is pushing OpenMP because yeah, by our multi-core introduction, and we are in the board of the OpenMP consortium, and so and it's easy. You don't need to change your source code. So if you want to get your application mapped to a multi-core architecture, you simply add a few directives. You don't change your source code at all, and this makes it very popular and very easy to use. You only have one source code base, some directives for OpenMP, and you're done. So, any other question? Okay then, thanks very much. So don't forget your t-shirt. Yeah.